Previously, we discussed Jacobson's theorem, which says that two Hermitian E-spaces are isometric as E-spaces. Hermitian E-spaces if and only if they are isometric as quadratic F-spaces. Remember, the setup was that E over F is a Galois extension of degree 2. Thus, Jacobson's theorem allows us to reduce the classification of n-dimensional Hermitian E-spaces to the classification of certain two n-dimensional quadratic F-spaces. We will use this idea now to classify Hermitian E-spaces over certain fields. We're looking at fields F such that the U invariant of F is less than or equal to 4. Remember that this is the maximum dimension that an anisotropic quadratic space over F can have. Which field has UF less than or equal to 4? Well, that include a lot of fields that we are familiar with. Finite field, we have for algebraically closed field, and we have function field in one variable. We will also see the p-adic field and fpx. Okay, so over such fields, so let's say F is such a field and E is a Galois extension of degree 2. Now let's say we have two Hermitian E-spaces that are of the same dimension over E, then they are isometric if and only if they have the same discriminant. Now of course, if they are isometric, then they must have the same discriminant, so we only need to show the other direction. So let's do that. We'll do that by induction. Now in the dimension 1 case, we can write V and W this way. Then we see that the discriminant of V and discriminant of W are just equal to alpha and beta. So to say that these two discriminants are the same means that alpha and beta differ by a square, because remember, discriminant is only defined up to modulo F star square. So if alpha and beta differ by a square, then these two spaces are isometric. Thus we are done. Now we're moving on to the case when n is greater than or equal to 2. Let's assume the theorem has been checked for smaller dimension. Now the dimension of V as a vector space over F is 2n, so that's going to be greater than 4. But as we said, the U invariant of F is 4, so if the dimension of V over F is greater than 4, then V must be isotropic, because 4 is the maximum dimension that an anisotropic space can have over F. Now V is isotropic, but V is also regular by hypothesis, so that means V must be universal. Because if V is isotropic and regular, it must contain a hyperbolic space. In particular, it contains a hyperbolic plane, so it must be universal because hyperbolic planes are universal. So it must represent, say, 1. So I will split out a component 1. But similarly with W, right? W must contain a component 1. Now the discriminant of V then is just going to be equal to the discriminant of V prime, and the discriminant of W is equal to the discriminant of W prime. So this means that the discriminant of V prime and the discriminant of W prime must be the same. And so V prime and W prime must be isometric. And we don't need to specify if it's isometric as Hermitian E-space or quadratic F-space because of Jacobson's theorem. So when V prime and W prime are isometric and these components are isometric, then that means that V and W must be isometric. So we see that for regular Hermitian E-spaces over such field K, if they are of the same dimension, then they are isometric if and only if they have the same discriminant.